You know, I have a friend who's an artist. He'll hold up a flower and say, "Look how beautiful this is," and of course I agree. Then he adds, "As an artist, I can see how beautiful it is, but you as a scientist take it apart and turn it into something dull." I think that's a little nutty, because I actually see more. I see the cells inside it. I see the intricate processes going on within, and that has its own kind of beauty. I see how the colors develop to attract insects so the flower can be pollinated. That's fascinating, because it tells us the insects can see those colors. So why am I talking about a flower when we're supposed to be talking about aliens? Because the universe is like that flower. When you look up at the night sky, you notice the beauty. You feel the silence. You see that endless black ocean, and your intuition, that wonderfully sloppy tool evolution built inside your skull, starts shouting at you. It insists the universe can't be empty. It's just too big to be wasted space. You do the numbers in your head, billions of stars, billions of galaxies. Even if life is rare, even if it's a 1 in a billion accident, there should still be millions of civilizations out there. They should be loud, they should be chaotic. They should be broadcasting I Love Lucy reruns across the spiral arms. So where are they? That's the big question, the Fermi Paradox. But I want to suggest that the reason we don't see them isn't because they're hiding or because they're shy. It's because the universe isn't built the way you think it is. The universe isn't a box. It's not a stage where you can just walk from one side to the other if you wait long enough. The universe is a machine, a strict, unforgiving machine, ruled by laws that don't care whether you want to chat with someone from another star system. We're going to open this machine up. We're going to look at the gears, and we'll discover that the same laws that allow us to exist, the same laws that hold your atoms together, are also the laws that slam the door shut and throw away the key. Let's start with the most basic illusion you have, the illusion of now. Picture yourself sitting in a room. You see me, I see you. We assume we're sharing the same moment. If I clap my hands, you see it happen. If something happens on the sun, we imagine it's happening now. Isaac Newton thought this way. He was a brilliant man, maybe the smartest who ever lived. He gave us a view of the universe like a giant clock. Tick-tock. Time on Earth was the same as time on Mars, the same as time near Alpha Centauri. If the sun vanished, Newton's equations said Earth would instantly fly off because gravity would stop immediately. Bang, instant. But nature said no. Nature played a trick on us, and it took centuries to understand it. It began with electricity. Think about a magnet here and a compass needle over there. You move the magnet, and the needle moves. How does it know? Is there a string connecting them? No. Is there some invisible fluid? No. Michael Faraday, a former bookbinder with little formal math but an incredible imagination, pictured lines of force. He imagined the space between the magnet and the needle not as empty nothingness, but as something real, a field. Think of a swimming pool, a huge calm pool. If I'm in the middle and splash the water right next to me moves. That pushes the next bit of water, which pushes the next, and so on. It takes time for the ripple to reach the edge. That's the secret. The field is real. The electromagnetic field is like a jelly filling the universe. When you wiggle an electron, you shake that jelly. A wave travels outward. We call that wave light. Here's the twist where reality gets strange. That wave in the jelly has a speed, a fixed speed. It depends on how stiff the jelly is and how heavy it is. In physics language, we call these the permittivity and permeability of free space. You can't change it. You can shout at the wave or shove it, but it still moves at its wave speed, about 300,000 kilometers per second. So if the sun were to disappear, the gravitational ripple in the space-time jelly would have to travel to Earth. That trip takes 8 minutes. For 8 minutes, the sun would be gone, but we'd still be orbiting nothing, orbiting a ghost, the place where the sun used to be. This delay isn't just a minor inconvenience. It's the fundamental speed limit of cause and effect. It's the speed of causality itself. If you could go faster than this, if you could send information instantly, you could tear the universe apart. You could send messages into the past. You could kill your own grandfather. The universe prevents these paradoxes by enforcing this limit. Now think about our aliens. Say they're in the Andromeda galaxy 2 million light years away. That means any news of their existence takes 2 million years to reach us. And it gets worse. It's not only about the delay, it's about the cost. Let's talk about energy. You've heard the equation E equal to mc2. Everyone knows it, but almost no one really thinks about what it means. It means energy is mass. Pick up a rock. It has mass. It's heavy. Now heat that rock up and make the atoms inside vibrate faster. The rock actually becomes heavier, not by much, not enough to feel, but enough to measure. The energy you added increased its mass. Now imagine a spaceship, a large, elegant one. You want to head for the stars. You fire the engines. The ship accelerates. You've added kinetic energy, the energy of motion. Since energy is mass, the ship has gained mass. It's heavier than it was at rest. You push again, it goes faster, and it gets heavier still. As you approach the speed of light, the speed of those ripples in the jelly, the mass skyrockets. It heads toward infinity. To push the ship all the way to the speed of light, you'd need infinite energy to move infinite mass. There isn't infinite energy in the universe. So you're stuck. You can get close. Maybe 99%, maybe 99.9%. But every extra decimal place costs more energy than the entire human race has ever produced. Nature is telling you, you can look, but you can't touch. I used to work with cyclotrons. We'd take tiny particles, protons or electrons, and spin them in circles using magnets. We'd kick them with electric fields. Faster, faster, faster. And what happens? As they approach the speed of light, they become so heavy that the magnetic field can't hold them in their circular path anymore. They fly out. We have to design the machines around the fact that an electron, this tiny speck of a thing, turns into a monster of mass. This isn't theory, it's engineering. We build real machines based on this behavior. So when people say, oh, aliens will have warp drives or anti-gravity, they're talking about magic. They're assuming the laws of physics are wrong. But the laws of physics are the most thoroughly tested ideas we have. The door is locked by the weight of the universe itself. But wait, you say, maybe they don't need to go fast. Maybe they just take a long time. Maybe they use cryosleep or generation ships. Okay, then we have to talk about time, and this is where your brain might hurt a bit. That's fine. It's suppose Ed 2. We think of time as a flow. The past is gone, the future hasn't happened, and now is all that's real. Einstein showed us this is wrong. Imagine a loaf of bread, or better yet, imagine a sausage, a long, infinite sausage of space-time. One end is the Big Bang, the other end is the heat death of the universe. The whole thing exists all at once. It's a block universe. You and I are slicing this sausage. Our now is a slice straight across, like cutting a cucumber. Everything in that slice happens at the same time. But if someone is moving, say an alien in a spaceship, they slice the sausage at a different angle. This is hard to picture, so try this. You're on a train, and I'm standing on the platform. The train is moving. You shine a light from the floor to the ceiling. To you, the light just goes straight up and down. Simple. But from my perspective, the train moves while the light is traveling. I see the light trace a slanted path up and back down. That path is a triangle. The hypotenuse of a triangle is longer than the vertical side. So from my point of view, your light traveled farther. But the speed of light is fixed. It can't change. So if it traveled farther at the same speed, it must have taken more time. Your time has slowed relative to mine. This means time is personal. It's private. My clock and your clock don't agree. Now apply that across the galaxy. If there's a civilization in Andromeda and they start moving toward Earth, their slice of the sausage tilts. What they consider to be happening right now suddenly sweeps into our future. If they stop and turn around, it sweeps into our past. We're not living in a shared reality. We're living in a collective ion of private time bubbles drifting through a four-dimensional geometric block. Because of this separation, contact becomes a very messy idea. By the time they see us, we might already be gone. By the time we see them, they might not even have been born. The universe is vast, not just in space, but in the way time itself disconnects everything. Okay, you say, forget spaceships. What about radio? Why don't we hear them on the radio? I love radio. It's just light you can't see. The same wiggling of the electromagnetic field, just slower wiggles. But there's a problem called the inverse square law. Imagine you have a can of spray paint. You spray a dot on a wall from 1 inch away. The paint is thick and concentrated. Now you step back 10 feet and spray for the same amount of time. The paint spreads over a huge area, but it's very thin. You can barely see it. Radio waves behave the same way. They spread out as a sphere. As that sphere grows, the energy gets thinner and thinner. By the time a radio signal travels just 100 light years, which is basically next door in our galaxy, it's already reduced to a faint whisper, and it gets worse. The universe isn't quiet. The universe is warm, not boiling hot, but it has a temperature. The Big Bang left behind a background glow. Stars pour out noise. Dust clouds radiate heat. Even the atoms in your radio antenna jiggle because of heat, and that jiggling creates electrical noise, static. If Thelian signal is weaker than that static, you can never hear it, ever. It is mathematically impossible to extract it. To send a signal that rises above the background noise of the universe across 1,000 light years, you would need a transmitter as powerful as a sun. You would have to shout so loudly that you would burn your own planet just to say hello. Would an intelligent civilization really do that? Would it spend its entire planetary energy budget just to check whether someone is listening? Probably not. They would stay quiet. Sin just like we do. And if everyone is listening and no one is shouting, the galaxy remains silent. Now let's look at the wreck. Us. I think this is the most miraculous part of all. We are atoms, hydrogen, oxygen, carbon, nitrogen, the same material floating in the cold, dead clouds between the stars. And yet these atoms have done something extraordinary. They have arranged themselves. In physics, we have a rule called the second law of thermodynamics. It says that systems naturally move toward disorder. Entropy increases. Build a sandcastle and the wind will destroy it. The wind never blows sand into the shape of a castle. Disorder is natural, order is not. And yet here we are, a collection of atoms so precisely organized, so astonishingly structured, that it can reflect on itself. Think about what's happening inside a single cell in your body. There are molecular trucks carrying cargo along microscopic highways. There are library systems reading DNA instructions. There are power plants converting fuel into energy. It is more complex than New York City, all packed into a blob so small you can't see it. For this to happen, for lifeless matter to wake up and become a civilization, requires a chain of accidents so long and so improbable that winning the lottery looks guaranteed by comparison. You need the right kind of star, not too large, or it dies too quickly, not too small, or it flares and sterilizes everything. You need the right planet. You need the right moon to stabilize the planet's tilt. You need a magnetic field to protect the atmosphere. You need liquid water. You need the spark of life. You need the jump to multicellular life, which took billions of years on Earth. You need to survive asteroid impacts. The chance that all these gates open in the same place is vanishingly small. Maybe the true barrier isn't just the speed of light. Maybe the barrier is the probability of existence itself. We might be the only ones who made it through. So we live in a universe where travel is physically forbidden by energy costs. A universe where time is fragmented and relative, making now meaningless across vast distances. A universe where signals drown in the leftover noise of the Big Bang. And a universe where life itself is a statistical miracle. Does that make you feel small? I've had students tell me, Professor, this makes me feel insignificant. We're just a speck, trapped in a bubble. And I tell them they're seeing it backwards. If the universe were crawling with aliens, if they were landing on the White House lawn, handing us cures for cancer and unlimited fusion power, then we would be nothing. We would be children, pets, a primitive tribe waiting for gods to rescue us. But if we are alone, if we are truly the only ones, then we are the most important thing that exists. We are the eyes of the universe. We are the way the universe becomes aware of itself. Without us, stars are just nuclear furnaces burning blindly in the dark. Without us, the laws of physics are just mindless machinery grinding away with no one to understand them. Being confined by the speed of light and the rules of relativity forces us to grow up. It forces us to solve our own problems. We measured the distance to the stars, not by traveling to them, but by thinking, by geometry, by parallax, by observing a star in January and then again in June and measuring its tiny shift. We learned what the sun is made of not by touching it, but by splitting its light with a prism and reading the atomic barcode hidden inside. We did this. Us, the jiggling atoms, the silence of the universe is not a rejection. It is a challenge. It is nature saying, I have given you a safe laboratory. I have built the walls so you do not destroy yourselves or get destroyed by others. Now show me what you can do. So go back to the flower. The scientific view doesn't take away its beauty, it deepens it. It adds the wonder of understanding how such order can arise from chaos. The same is true of the sky. When you look up, don't wish for spaceships. Wish for understanding. The aliens are not coming. The door is locked. But, look at the room we are in. It is a magnificent room, filled with light, gravity, particles, and fields. And the key to understanding it all is already in our hands, in our equations, our experiments, and our curiosity. We don't need them. We have ourselves. And if you really think about it, that is enough. That is more than enough. If you want to stay in this room with us, if you want to keep exploring the machinery of reality, subscribe and join us. We'll keep taking the watch apart until every gear is visible. Thank you for listening. Now go outside and look.